In this video, we're going to talk about frequency. So frequency is the number of times a data value occurs. Pretty simple definition and straightforward, but powerful. We can get a lot of information from it. So let's look at this example. 20 students were asked how many hours they worked per day, and their responses in hours are as follows. Okay, so we have this list of data, but it would make sense to count up how many people said 5, how many people said 6, and so forth. So I can see just by kind of scanning the list that the lowest data value is 2. So I'm going to put that first. And it looks like we do have a 3, 4, 5, 6. And the highest value is 7. Now, if any of these happen to be 0, that's fine. It would make sense to go ahead and just go right in order 2, 3, 4, 5, 6, 7 and put a 0 then for the frequency if nobody said that data value. We don't have that in this example, but it wouldn't be weird to do that. Okay, so I want to count up how many people said 2. So it looks like 1, 2, 3 people. For the 3s, it looks like 1, 2, 3, 4, 5 people. For the 4s, 1, 2, 3 again. For the 5s, 1, 2, 3, 4, 5, 6. 6s, looks like there's 2 6s and 1 7. Okay, cool. And I should add this up, make certain I got 20 because that's the total, right? They talked to 20 people total, and I should add that up just to make sure that I do in fact get 20. Oh, I'm sorry, I wrote a 7 instead of 1. Wow. So I was adding it up in my head. I'm like, wow, that doesn't add up to 20. Well, there you go. See, now you learned from me to make sure to add them up and that they add up to the right number. Okay, now this next column says relative frequency, and actually the definition for that is right below. So a relative frequency is a ratio, or it could be thought of as a fraction or a proportion, those are other words for ratio, of the number of times the data value occurs in the set of all outcomes to the total number of outcomes. So in other words, for hours per day worked of 2, there were 3 people out of 20. That's how you would write the ratio of that. So that's how we write the relative frequency. But you'll notice that below, it does say you can write it as fractions, percents, or decimals. A lot of people favor thinking of it as a percent or a decimal because it kind of makes sense to see how the data is split up among the categories. So 3 over 20 as a decimal is 0.15 or 15% if you want to write it as a percentage. 5 out of 20, that's going to give me 0.25. I encourage you to divide those on your calculator. And in fact, I would even pause the video, do all these calculations real quick, and then check it with me and make certain you got them correctly. So 3 over 20 again is 0.15. 6 divided by 20 is 0.3. 2 divided by 20, that's going to come out to 0.10. Or 0.1, you don't have to put the 0. I'm just kind of thinking of them as percentages. And then 1 out of 20, that's going to come out to 0.05. All right, so there we go. And those should add up to 1, because if we're talking about percentages, it should total to 100%. Cumulative relative frequency, this is the accumulation of the previous relative frequencies. To find the cumulative relative frequency, add up all the previous relative frequencies to the relative frequency for the current row. The last entry of the cumulative relative frequency column is 1, indicating that 100%. So it's like constantly taking the previous data and including it. So for the first data row, 2 hours worked, it would still be 15% or 0.15. But for when you're talking about 3 hours work, I'm going to take that 0.15 and I'm going to add it to the 0.25 that I have here in the relative frequency column. So I'm going to be adding those two together to get 0.40, which means what that's representing is that 40% of the data is less than 3 hours or 3 hours work per day or less. So 40% of people said they work 3 hours a day or less. So for the next one, I'm going to add the 0.15. I'm adding up all three of these, this one, and this one. So that's what I'm doing. I'm adding up all three of those. So that totals up to 0.55. Or we're saying that 55% of people who answered worked 4 hours or less per day. Then adding the 30% is going to give us 0.85. The 10 is going to be 9.5. And the last one is going to be 1.00, or just 1 for the 100% that we have reached. Now, I do keep kind of talking about decimals in terms of percents, and we do use them interchangeably in statistics. So when I see 0.15, I can think of that as 15% pretty readily. Okay, so we're going to kind of look at a different type of example. And in this example, I actually kind of just listed below the data that we're looking at. This is called grouped data. So this is data that is organized as intervals. So we're talking about heights in this example that are going from 59.95 to 61.95. So it's an interval of numbers. They also call those intervals classes. That's another term they use, classes. And so because we have classes here, just to kind of make sure we understand, so this would be, there'd be the first class, second class, third class, and so forth, for a total of 7 classes. Okay. Now, the class width is the difference. Now I'm going to zoom in just so I'm making it neat. It's the difference between consecutive lower class limits. So before I make sense of that, a class limit is referring to the interval numbers. So the lower interval of the numbers, these are all the lower class limits. And these are all the upper class limits. So the difference between consecutive lower class limits, it also works for upper class limits too, by the way, but just for the ease of the definition, that means we're taking the difference between these two numbers. So 61.95 and 59.95 is a difference of 2. In other words, if I add 2, I'm going to get to the next lower class limit. And it works for upper class limits. These are also differences of 2. That'll always happen. That's not a coincidence. And that's what the class width means. The class midpoint, because sometimes you see that terminology too, is the average of the upper and lower class limit. Meaning adding the 2 together and dividing by 2. We'll see that here in this next example. So now to put it into context, let me go ahead and zoom out a little bit. We're talking about heights of soccer players, 100 semi-professional soccer players. Okay, so these are representing heights, and each height, we have a frequency for each category. So let's go ahead and fill in the relative frequency for all of these. So if we were to total the frequency, it's going to be 100. I know that because they told us it's a sample of 100. And therefore, the relative frequency, when you divide 5 by 100, it's just going to be 0.05. 3 is going to be 0.03, 0.15. In other words, we're basically turning all of these into percentages. So go ahead, and I would encourage you to pause the video and calculate all the cumulative relative frequencies but I'm going to go ahead and go through that real quick, and then we're going to answer a series of questions. So the cumulative relative frequency for the first category always starts off as the same as the relative frequency. The next one, we're going to be adding the first two together, the 0.05 and the 0.03 for 0.08. The third one, we're going to be adding the first three together, 0.05 plus 0.03 plus 0.15, coming out to 0.23. Adding 0.4 will be 0.63. Adding 0.17 is 0.80. Adding 0.12 is 0.92. 7, 0.99, and then finally we reach 1 for 100% of the data being less than 75.95 of heights in inches. Okay, so we're going to use this here. I'm going to zoom out just a little bit more so we can kind of refer to it to answer these questions. So they ask us some questions about this data using this information. So they want to know the percentages of heights that are from 67.95 to 71.95. So 67.95, going up here to the table, I see 67.95. I see it here and here, right? I see it in both places. But they want it to be from 67.95 up to 73.95. So I'm going to go ahead and ignore that. Oh, by the way, I see this note here. All the heights fall between the endpoints and not at the endpoints. So I noticed, you might have noticed that the upper limits for the previous class match the lower limits for the next class, but it's not a problem because nobody's actually going to be recorded as 67.95 inches. So they're actually between these two values. So nobody's going to be those values at all. All right. So 67.95 up to 71.95. So basically, we're going to have to do data for these two classes because the data for the first class is from 67.95 up to 69.95. And then it picks up again from 69.95 to 71.95. So that is a total of 17 and 12%. All right. Which gives me 0.29 or 29%. So since they actually asked for a percent, I'll write my final answer in percentage form. Okay, so now they want to know the percents of the heights from 67.95 to 73.95. So that's actually going to include the same two categories, but then it's going to go up one more category to here. So we're going to look at these three categories. So we're adding the 0.17, the 0.12, and the 0.07 for a total of 0.36 or 36%. So if this makes sense to you, go ahead, pause the video, fill out the rest on your own, and then compare your answers with me. So percentages of heights that are more than 65.95 inches. So we're talking about every category from here on, right? All of those categories. So we're going to add up all of those percentages from here to here. All right. So 0.40, 0.17, 0.12, 0.07, and 0.01 will give us a total of 0.77 or 77%. All right. Now, the next one, I'm going to scroll down and I'm going to have to scroll back up to look at the table. So the number of players who are between 61.95 and 71.95. Now, notice this is a different question. They're not asking for a percent. They're asking for the number of players. So they're asking me for the frequency. They want to know how many players who are between 61.95 and 71.95. So here, let me erase that. So 61.95 and 71.95. So there we go. Those players right there. So that's 3, 15, 40, 17, and 12. All right. So we're going to add all of those up, and that totals up to 87. And that's the answer. Just 87 players. Okay. What kind of data are the heights? So this data would be considered Quantitative continuous, that's one classification. Oops. Quantitative continuous. But the level of measurement classification would be ratio. However, our book favors the qualitative, quantitative answers. So we will be primarily using qualitative and quantitative as our levels, our way of measuring data and classifying data. And only when we're told to use the levels of measurement will we switch to the nominal, ordinal, interval, and ratio. Okay. Describe how you could gather this data, the heights, so that the data are characteristic of all semi-professional soccer players. So basically, we need a random sample. And if we're talking about this type of data for a semi-professional soccer player, this type of data is probably pretty straightforward and probably collected pretty easily. But we would probably contact some of the coaches, right? And I think it'd probably be easiest just to do a simple random sample. The reason is we're talking about a pretty homogeneous group of individuals. Um, Now, if we're worried about maybe ethnicities or anything like that, I still think that most teams you're going to see a pretty good ethnic blend regardless of where they're located, just because of the type of players who are interested in playing soccer. So a simple random sample will probably be pretty safe. We'll see a lot of common characteristics, and I don't know if we need to. There might be an argument for some sort of cluster or stratified, but I think a simple random sample is pretty easy. We contact the coaches and get the rosters from them, and then go ahead and ask each of those players for the heights.